I'm Rob.
And we're both Princeton graduate students, and our research group is studying a special type of quantum material known as a two-dimensional or 2D material.
But Grace, what makes a quantum material quantum? And why are you dressed like a Ghostbuster?
Well, quantum is the new hot sciencey word. There's quantum tunneling, quantum toothbrushes, and even quantum beer. It's even in the movies, like a personal favorite of mine, Ghostbusters.
Sure, but back to the main question. What is a quantum material?
Well, the definition of a quantum material varies from scientist to scientist, but most agree that the phrase quantum material is an umbrella term that encompasses materials that exhibit anomalous or interesting properties, which means that we need to use quantum mechanics to describe them. We can't just use classical physics or theories. But the most important part of quantum materials is that it's brought together chemists and physicists under a common goal of trying to figure out why they have these special properties and how we can use this information to our advantage.
So, okay, we have interesting materials with abnormal properties, but are they good for anything?
Quantum materials have been around for quite some time, and you've probably interacted with or at least heard of quite a few, such as the superconductors found in the maglev trains, or magnets, which can be found in most electronics. But the one that I wanted to talk about today, and that is fairly recent, is 2D materials. 2D materials were discovered in 2004 by Novozolov and Geim when they managed to rip a monolayer of graphene off of graphite just using Scotch tape.
So what makes a 2D material a quantum material?
Because 2D materials are so incredibly thin, you need quantum mechanics to describe their properties. Quantum mechanics usually becomes very necessary when things get very small. And like quantum materials, 2D materials don't have a hard and fast definition. However, something is typically considered 2D when it's about 1 to 3 layers thick or 1 to 3 nanometers. To put that in perspective, a single sheet of paper is about 100,000 nanometers thick. So 2D materials are very small.
So you have a smaller version of a larger thing, but what's the point?
The point is, now we have even tinier electronic materials that we can work with to make smaller, more conveniently sized technology. But even cooler than that, it turns out that when you exfoliate materials down to the 2D level, their properties don't always stay the same. They can improve or even completely change. And this is in general due to the in-layer properties overtaking the out-of-layer ones. And this leads to what are known as layer-dependent properties. And this allows us to finely tune the material properties layer by layer, just the way we want them. And between the small size and the high tunability, the applications for 2D materials are infinite. And this ranges anywhere from electronic clothing to better biosensing.
So this sounds great. Why don't we just Scotch tape everything?
It's not that simple. It turns out trying to exfoliate something down to the 2D level can be pretty problematic, and Scotch tape doesn't always work, which means we need to get creative with our exfoliation techniques. And the simplest way to start off is by using an already layered material. Like onions and layer cakes, materials can be made up of layers of repeating units with space in between those layers, held together only by weak interlayer forces. This allows us as researchers to have an easy plane in which to exfoliate on. And now that you've picked the material, you have to do the actual peeling. So Novozolov and Geim used Scotch tape, which is known as a mechanical exfoliation method. However, since then, many other techniques and methods have been developed to tackle more problematic materials, such as chemical exfoliation, which is what I study. Chemical exfoliation typically consists of a layered material, and you intercalate or insert an ion in between those layers, expanding that interlayer distance. This allows us to use shaking or sonication to gently remove those layers, resulting in a nanosheet. This technique can be easily tuned just by adjusting the ion, the liquid used, and even the sonication and shaking times. And the better you tune the method to the material, the better your results. And by further developing these exfoliation techniques, we can expand our library of 2D materials, giving us more quantum materials to work with to build the tech we've always dreamed of, limited only by our creativity rather than size.